Hello everyone, I am Dr. Jayasingh, coordinator of CE201C. This is another video lecture and this will going to cover the deflection of beams. And this section or this deflection of beam section mainly contain three components. The first part in here we're going to study about how we're going to derive equation to get slope and deflection of the beams by using integration method. And the next one, this next component, we are going to talk about like a Macaulay's square bracket notation. This one normally we going to use to create a bending moment equation. So I will explain clearly where we can use this square bracket notation. Actually, this is a mathematical part and where we can use it and why we need to use this square bracket notation. And the last component we're going to touch about the moment area methods. Yes, in here we are going to use the derived equation based on actually this is differential equation. We're going to derive the differential equation to get slope and deflection, and that means like we can get continuous variation of slope and deflection along the beam in this way. But in this moment area theorem, actually we are going to we can see there is like a two theorems, theorem 1 and theorem 2. Theorem 1 basically used to get the rotations, and theorem 2 for deflection. And this one we cannot obtain continuous equation, continuous varying equation. If you need any specific point of beam, we can obtain deflection and slope. These are the main three components. First one, we're going to derive the equation, and that is like partial differential equation, not partial differential equation. This is just straight differential equation. And after that, next one about like how we're going to use square bracket notation for derive or present moment of beam, and third part going to cover moment area methods. That's also the part of this deflection. Okay, now we can shift to our first component, and this is our first component and deflection. Yes, the deflection, when you come to the deflection, it is actually somewhat different from our previous previous sections. In the previous section, mainly we focus about beam, of course, about beams, bending moment, shear force, and somewhat about axial forces. We go and go the end, and we estimate these values, and based on this one we try to check the shear and normal stress, and after that we focus about how we're going to vary with the cross section these things, and the final presentation explain about in the planes, inclined plane, how we're going to change this one. That means simply these things basically work with strength of the beam, strength of the your beam system. But in today we mainly going to focus about some kind of serviceability criteria. That means in here the deflection going to cover actually serviceability criteria. These are going to cover strength of the beam. When you come to the design stage, mainly we can see two components. One we call ultimate design, ultimate limit state designs. Another we'll call the service limit state design. So under this one ultimate, we are going to check the capacity of the beam based on these parameter: moment, shear force, and axial forces basically. And the serviceability, when you come to the serviceability, in here we're going to check about how about like under service condition, how about like comfort levels. Under that one we're going to check about the deflection. It's like something like here. So think about, you have this kind of beam, and think about this has a support like this. Okay, and think about we are here, one person here, and based on you can calculate the required bending moment and shear force and axial force. Think about it is okay, so it's not going to fail under the strength criteria: moment, shear force, and axial force. But if this beam think about the deflection is so high, delta, we call the delta, is so high, then actually what you feel, it's not comfort. Of course, we know this is not going to fail because of it is okay with this strength criteria, but deflection wise it feel uncomfortable for you. So that's the thing here today we're going to discuss. So this is related to your service condition. So in the under service condition, how this system behave. And if we have like a high deflection, of course, like some as this as example, so you may not like to stay in that kind of system, so you may don't like. So two things we need to consider. One we call ultimate. Yes, it will come with these parameters. When you come to serviceability, of course there are some other parameters. The main one is deflection. You need to check. Of course, when you come to static, of course deflection. And if you come to dynamic system, you need to check about like acceleration and velocity variation also. Okay, so now we can shift to this part. Before you shift, we shift to directly for formulation of this deflection and rotation equation. We should know our simple formulation based on the simple bending formulation, because this simple bending formula we're going to use for formulate this our deflection equation. So we know this one. I'm not going to explain again and again. So the main assumption is plane section remain plane. So you know what actually happened. This is before deformation. Then you can see this is longitudinal axis, and you can develop the planes or otherwise layers, and this cross section, this plane is perpendicular. You can see that one directly. These are perpendicular. These are perpendicular to this longitudinal direction. And what this mean, plane section remain plane after the deformation, means like after this is under pure bending. Okay, pure bending. After this bending, also what we can see these are perpendicular to each other. Okay, these are perpendicular to each other. Of course, now you know about like the shear effects, and this simple bending formula normally going to represent, or otherwise we can use another name for this one, Euler-Bernoulli beam theory. Both are same. So Euler-Bernoulli beam theory means actually this is we call Euler-Bernoulli beam. So Euler-Bernoulli beam means it's like a slender beam. So think about height is like I will put this length L and this is H. If at least if L is, I will put like this name now, L is should be greater than at least 3 times, actually I put at least 5 times H, at least this much. So then if we have this kind of arrangement, we can call this one for slender beam. So slender beam we can give another name, that means Euler-Bernoulli beam. This Euler-Bernoulli beam slender, that is going to deform mainly from bending or flexure effects. That means we are not going to consider this under this beam theory. We are not going to consider any shear deformation. Okay, so if you know now from previous lecture, if you have like shear deformation, you can see Wolfing effect. So that means this going to shape like something like this. But here we are working under pure bending, so simply this beam going to bend mainly due to flexure effects. So we can neglect shear component. If we going to neglect shear component, so we can assume plane section remain plane after the deformation. Or otherwise, actually we cannot assume, or we cannot approximate like this. So I will clear this one first. And the next beam, this is a Euler-Bernoulli beam. So we got slender beams. Other one we call the deep beam. Deep beam. Here we are not going to touch this type of beam. Deep beam, actually very short beam. Okay, so this is H and this is L. So at least think about L should be less than 3 times H, 3 to 2 times H. So if it's less than this type of thing, so we call the deep beams. In the deep beams, of course, we need to consider shear deformation as well as flexural deformation, both. And if we come up this way, so then we cannot assume plane section remain plane. So that's why this is a little bit complex actually. Handling this level is a little bit complex. So we are not going to touch this kind of deep beams, because of in here we can see both deformation due to shear and due to flexure or bending. So we are not going to touch this one in this course. We basically work with slender beams or otherwise Euler-Bernoulli beam that going to behave or that going to behave under simple bending theory. Okay, so now this is a main assumption. So we already have good discussion about these things, so we don't need, but better to know this thing again and again. And when you come to the here again, the most important things, one thing here plane section plane plane, and other one most important thing, we are working with small deformation. So when you come to the small deformation, we can simply come up with this kind of approximation. So that means first derivation of your V is a deflection. So first derivation of deflection give tan theta according to this figure, but in this we are working with very small deflections. So because of that, this theta tan theta we can assume to theta. So again, that is come with small deformation. But when you come to large deformation, yes, you cannot assume like this. Okay, keep in mind those things. And we can see other assumption, of course, material homogeneity. Of course, there should be homogeneity, and so simultaneously we work with like a linear elastic stage. Consider only small deformation. That's most important. Next part. When you come to large deformation, is totally different, and small deformation and small rotation under prismatic beam, uniform beam. Consider only pure bending due to bending of flexural behavior only, and we're not going to touch about shear deformation. Okay, so those are most important part when you're going to use Euler-Bernoulli beam theory, or that's the same simple bending formula. And sign convention, this is you already know, we call the Hawking positive. This is for bending moment clockwise, shear positive, that's also you know. When you come to the deflection, that's the new part. Normally we work with in here, generally we are working with beams. So beam generally what we can see loading in top part, and we can see the deflection downward direction. So because of that we are using downward positive. Okay, but it depend on in your textbook. If I am correct, they are using upward positive, based on their sign convention. Okay, careful about this thing. In here we are using clockwise positive rotation. So in here the clockwise rotation positive. You don't need to confuse with this one like the previous section about Mohr circle. Of course, Mohr circle we use anti-clockwise. It depend on the case where we use, and under this consideration or this section we are going to use the rotation when it comes to the clockwise positive. That is just sign convention. It's not going to affect your values. Okay, and same time if you can visualize this in like graphically or figure wise, so then you don't need to worry about too much about sign. You know which direction is going. So simply you need values to explain such a things. Okay, so we can shift to next one. So this is basically about like a flexure formula. It is not new thing actually. So we can use to develop a flexure formula from simple bending formula or Euler-Bernoulli beam theory. So in previous lectures we used these two parts, and we work with normal stress variation and with cross-sectional dimensions. So you already know about those things clearly now. In here, under flexure formula means like we going to work with these two components. Okay, these two components, and basically when you come to here, so we can rearrange this one as this. So you know this part. What is this part? We call the curvature. So curvature means like after deform your beam, so any point you can get the radius radius of curvature, this is r, and 1 over r define the curvature. It's like mathematical terms. And this is a radius. Of course, in here we are expecting beam to behave, or beam to we are expecting very small deformation. Due to that, our r is normally very huge. If r is huge, this actually is almost like a is going to zero. If it is r infinite, of course it's zero. The straight line, of course, is 0. 1 over r is finite, but not actually 0, but it's almost near to 0. Okay, so when you're going to derive equation, we are going to use this kind of assumptions. Okay, and we should know what kind of system we are dealing here. We are working with beam, and we are expecting small deformations. Actually, most of the case we cannot see from our naked eye. So actually, if you need to see this kind of things, you need to do the measurement, or you need to use at least a theodolite or something to check the deformation of real beams. So because of that, we are working with actually r is so huge. So then compared to your beam, length, it is large, and that means 1 over r, it's almost near to the 0. And other components in here, so we already know. So m, what is a bending moment? I, it is like a what we call bending moment, or actual second moment of inertia of your cross section above the neutral axis. And 1 over r, again, that's a radius curvature, and the radius of curvature is r. So this part, actually, books and notes, they are referring that part as a curvature Flexure formula. So now this is directly we're going to use it. And what actually we're going to do in here, so we're going to formulate uh, the differential equation, to obtain deflection and rotation of beams. Okay, so for that we are going to directly use this Flexure formula. So next most important things, and this part also and this is about like equilibrium of infinite small element, and this is actually part of beam. And think about, you have beam arrangement like this with think about anything, and this is very small component. Okay, come to here, and this is again under bending, and we can see this is m. After dx component, dx distance is like m plus dm. So we already derived this equation, so in our first few lectures, so you can go through again. This is, I'm considering equilibrium in this direction and getting the values in this code equal to dx. You know the definition of this one, so you can see your shear force diagram, slope of your shear force diagram is going to equal minus opposite of load intensity at that particular point. And same time, you can derive this equation, you can take moment about a axis, a point, and you can end up with this equation. This means slope or variation, slope of bending moment diagram with respect to dx is going to equal minus your shear force at that point. So these two equations also we're going to use. Now we have like a three set of equation. One, we call the first equation Flexure formula, and this is again about like a radius of curvature and actual curvature, and this is about the relation with the shear force and load intensity. This is about moment and shear. We're going to directly use these things to formulate our this deflection equation. Okay, so now we're going to jump to this one. We're going to target about beam, deflection, and same time rotation. Rotation is like a tangent, how much is like a theta. Of course, you are getting actual tan theta. In here we are talking about very small deformation, so because of that is going to equal to theta. And by this is we go into integration formula. Okay, so what we're going to do, actually we are going to derive, or we're going to take out, this is our deflection dx some power, I don't know which power we end up with, some value, And after that, that means if you need to take this one, this straightforward deflection equation, what you need to do integration respect to these values. Okay, so by integration you can end up the solution to this deflection and same time rotation. Okay, so come to here. Now I'm directly jump to this part. I'm directly give the definition for curvature 1 over r. This is actually from the mathematics. I'm not going to explain how you're going to derive this one. This is something think about. If you have function fx, think about like it's curve, and any curve, it can be any curve function, and any point curvature, it will explain like this. Okay, any point curvature on this fx function will explain from this equation. Okay, so now from our first equation is this one. We know this is curvature. Okay, this equal to m divided by ei. Actually ei has a different name, not a different name, but actually special name. We call this one to flexural rigidity. Okay, so again we're going to call this equation 1 and substitute this one. You will end up with this equation. And this one again you can rewrite this way. How we going to rewrite this one? This part we can represent v double prime. This one we can represent e prime. Same thing, different notations. Okay, this is your equation. Okay, but when we consider, this is of course when we can work with this one. This is exact solution. Except not exact solution. I cannot tell exact solution. This is a solution, more accurate solution for your system. But when you're going to work with this one, this is a little bit complex. You can see if you're going to integrate this one, both side it will have problems because of upper and downside. You can see it's a mix of second order and first order differential, so first order and second order. So it is not easy to work. And same time when you're going to work with engineering problem, we are working with engineering problem. So and same time we know about like a beam system. We are working beam system. That beam system has very small deformation. So due to that one, our v prime, otherwise dv over dx, very small compared to this one. Okay, so very small compared to 1. So that means 1 plus, and again this is square root of that part. So we can assume this one simply 0. Okay, assume simply 0. Now based on that assumption here, you can see that assumption here. Based on this assumption is going to 1, totally 1 plus this part going to 1, and you will end up with very simple equation. Don't ask why we are doing this one, and this is basically we are doing considering this special beam cases. So on our beam cases, we cannot see very huge deflections. That's why I'm again and again saying this is only for small deflections. Our beam theory all are valid for small deflection deformations. So if we have a small deformation, you can simply get this one, actually this part v time we can assume is very small, and that means v prime squared, it's again very small. That means it's plus 1, it's going to 1. So simply it will end up with this one. This is the equation that we expect. Now we know this is related with m. M is bending moment at that particular point, and this is a v double prime means the second derivation with respect to distance. So okay, so now we have differential equation. It is like a second order differential equation. It's a straightforward differential equation. You can solve it. What you need to do, if we need to take rotation means y prime, so you need to take integration with respect to x. If you need v, this is a rotation, and this is a deflection or deformation of your beam, and you need double integration with respect to x. Okay, so basically using this equation, now you can get the variation of theta. Theta means slope, and the variation of deflection, that means simple v. And same time we can modify this equation by using your equation number 3 and equation number 2. Equation number 3, you can go equation number 3 means this equation, and equation number 2 means this equation. So we can start from here. We know that now equation, some equation for bending moment, and you can convert that equation to relation with your deflection relation, your deflection related to shear force. If you know this one, you can shift here and you can create a equation or expression for your deflection variation with load intensity. Okay, so this is the same things we are doing. We are going to equation number 3 and you will end up with this equation. This is third order derivation, third prime, you can see, that means in here third derivation, sorry, I will put it here. This is a third derivation, so with respect to x we x3, and this is a fourth derivation. So that means simply you can see, if you need to find deflection of your target beam arrangement, you can start from this equation. That means like you need to find the general bending formula for your section, and you can substitute, and you can apply integration with respect to s, and you can end up with theta and v. Okay, that's the first way. Or otherwise, if you know, you can start from shear force, or the main way of using this one, you can start from here. If you know load intensity of this, then you can apply the load intensity here, you can replace, and you need to end up this one, integration. So first one you will end up with third order, second one end up with like a second, third one and fourth one will give you a rotation and deflection. So you need to end up with like a 4 integrations. Up to you. If you feel it is comfortable with you, so though you can start from here, but in most of our cases we are going to start from this level. In here again you can ask, this is a distributed load intensity we can define. What actually happening if you have like a point load? So that is actually here I'm not going to explain. Actually we can deal with these things like a delta function. This is like a mathematical, actually this is mathematics. Okay, this is mathematics. In here you need to introduce mathematical, so delta function for this one. So delta function definition, please go in the internet and try to find out, and you can, and same time I hope in from your previous mathematics subject they covered this part. Please check it, those things. You can introduce delta function for here, this component, and you can do it. Okay, but in our case mainly we're going to work with this one. I will show you how you're going to work this one if you have like a pure UDL or uniformly distributed load only, not for delta functions. Okay, and now you are clear about what you need to do. In here what you need to do it, and you are come up here, and after that you do integration. If you come like a true integration, you will end up with theta and your displacement, and of course this is open integration. So then you will end up with constant, we call the integration constant, and when you come to here we can see 2 integration constant, 2 time integration will end up with like a 2 integration constant. These things are you going to find. Of course, how you going to find this one, we need to apply the known values and you need to fix this integration constant. So these known values we give the different names, so we can use a name as boundary conditions. So we going to apply the known boundary condition of your beam arrangement to find this integration constant. Okay, so we'll see. And this is equation, this is equation. Now we know you can start from here or here, up to you. In C0, CE201, basically we're going to start from here. I will show you some example for this part also. And here again I'm telling this one, we are using theta means slope, and going to represent v dash is going to equal to theta. Actually it's not 100% equal, it's like approximately equal to theta, and this is about the sign convention. So when you come to here, this is already know, this is actually our beam, and we deform like this under hogging, and clockwise shear is correct, and deflection we are taking downward direction. Okay, downward direction, and clockwise rotation is positive with this axis. Axis means like a left to right. We give the definition for positive axis, and this one to this rotation we call the theta. That's really this way. And when you come to the here, so if you can define, this is for this course, okay. Under this course, if you use different textbooks or different books, please refer this sign convention first, otherwise you will get a confuse, okay. And if you define like this bending moment, this positive and this manner, so we are going to define then this radius of curvature as a positive. So that means if we have this kind of arrangement, so directly you can apply. That means like if we are applying positive bending moment, that means like hogging, these values gives positive values. Okay, simply that's the meaning of here. So if you're going to define this manner, you all things, then automatically your radius component, this radius component will come positive. You don't need to worry about sign. If you have the minus, it automatically comes the minus. Okay, so that means if we are applying the positive bending to here, so this component positive. If you're going to apply negative bending for here, that will like a shagging, so then it will become a minus. Okay, so it is only for this course, but if you're going to refer any other books, especially your textbooks and Hibla books, so it will go opposite most of the cases. Okay, please carefully you need to check those things. Okay, now we will see how we're going to use this equation to find this one. First we will check about like a boundary condition. So here explaining solution for any above equation successive integration. Of course we need to follow integration methods to obtain the deflection and curvature elastic curve. For each integration it is necessary to introduce a we call the integration constant of integration, and then solve for all constant to obtain unique solution for a particular problem. So this one we can need to use a boundary condition. It depends on your system. When you come to roller, again what you can see the displacement. This is delta referring displacement 0, and we can see moment of course 0. Sometimes we are using, actually these are the primaries, these are the secondary boundary conditions. Primary means we categorize primary under primary category, so we can see deflection and rotation. Secondary we can see bending moment and shear force. Okay. So in here what we can see, deflection 0. If you like to dealing with bending moments, then of course it's equal to 0. Pin same you can refer, and the roller of course same. And here we're going to tell anything about bending because this is the intermediate point. And here same, we cannot tell, of course it's not going to transfer any shear. So bending moment, sorry, it's not going to transfer, sorry, it will not going to transfer any moment to this side to this side, only it can transfer shear. But we don't know anything about deflection. It can deflect like this. This is the intermediate point, okay, and this is again the intermediate point, and here we only know about like a deflection, and rotation we don't know. And here the fixed end, yes you know, rotation and deflection 0. We don't know anything about bending moment and shear force. Okay, and if it's a free end, so we don't know anything about like a rotation and deflection. We need to calculate those things, but we 100% know shear and bending moment going to 0. So these are known values. Known values we call the boundary conditions. Okay, based on your system you need to find, and after that you need to apply for these integrated equation, and you need to find this integration constant, and after that you can fix the, or you can find general solution for v and theta. V means deflection and theta means slope. Okay, we will see from now. We're going to shift example. Here in this category I'm going to do actually around 5 examples, a bit more example. So I tried to cover all type of different question under this category. Because of this huge example, I'm not going to discuss in detail your tubes under this category. So almost integrated to here. Okay, so please go through this handouts and this video lecture of my explanation and try to understand clearly. Okay. So when you come to the first question, and all what we need to do here. So we have system, we need to find the bending moment, and after that we need to use our equation. Of course, I already explained we are normally using this bending moment equation to find this v and theta, and after that you need to do the integration. And the one most important part is in here we can express our bending moment through one particular equation. One equation, any correction, anything, anywhere, we can express that bending moment through one unique equation. So if we have different set of, think about like if we have like this kind of arrangement, then of course you need to derive the bending moment equation for this particular point separately and this particular point separately. Then you cannot apply this your equation directly. You need to use portion by portion. I will explain this kind of example later, but first I am going to jump. If we have one section, that means like if we can express the general bending moment arrangement for a particular point by one equation, so how are you going to deal? And this one I will talk later. We have two system or two bending moment arrangements, so what we are going to do it. Okay, in here simply we can see we can express in one bending moment equation, and you can get the cut section from here. You can take the results. You can consider either this side or either this side. If you're going to consider this side, you need to find the reaction forces and bending moment. So otherwise, if you are going with this section, you don't need anything. So you just can apply, but careful about the length. So then the length will be L minus X. Okay. So come to here, and you can get the bending moment. And please substitute this equation, your known equation now, and you will end up with this differential equation. Now you can see this is second order. So now we are targeting v and v prime. So to get to v prime, we need one integration, and to take v or deformation, so you need two integration. Okay, so we'll see now. So equation 2. So equation 2 means this one. We're going to integrate with respect to x, assuming, of course, I need to mention this one, we are assuming ei constant. Otherwise, actually, we are in trouble. If you're going to integrate this one in this manner, so if ei is going to change, that means, think about if we have this kind of beam, think about this kind of arrangement beam. So think about this is ei, this is 2 ei something. So then you cannot apply this equation for whole domain one shot. Okay, so then what you need to do, you need to go again part by part. This is equation. If you have this kind of arrangement, you are struggling, so you cannot integrate, it's going to change. So 0 to L you cannot apply, so part by part you need to go. So in here actually I'm assuming it's a uniform beams, so then ei is like a flexural rigidity, we can assume as a constant, so we are going out. Okay, so we take out, and this is v dash, and you will end up this one. Of course I'm not going to explain how you're going to do the integration, that's a simple thing from A level. So you will end up to C1. This is integration constant. And now what you can do, like this equation, you can integrate one shot, and you will end up with this one. Of course, you can see this is a theta rotation component. Actually, this is dv over dx. That's really equal to tan theta. But tan theta is so small, so then it's going to theta. Then mean actually v prime going to give you some idea about the theta. And this is a deflection. Now based on your system, we are talking about cantilever arrangement, so we know this is fixed. So if it is a fix, these two going to 0. So that means rotation at x equal 0 0 and deflection at x equals 0 0. So you will have these two values, and please substitute this value to this equation like this. So you can work with the third one about rotation. So apply this one, you will end up with C1 equation, C1 value, and now you already know C1. Of course, C1 you don't need because of this is 0 again. This multiplication is again to 0. And from the fourth equation, apply this boundary condition and you will end up this value. So now you already know, and please substitute this value for your equation number 3 and 4, and you can get variation of v with respect to x, theta, or slope, rotation with respect to x. And we can simplify like this. Again, I'm asking, so these are my calculation method, of course correct, but please check these values. Okay, now according to this example, I'm asking find a tip. Tip means this one, tip, deflection and rotation. Of course, at that point, when we are going to do any deflection problem, so first I think better to visualize your deflect shape like this now. So I will erase these things. So first visualize, then you can see. Actually in this one, if you're going to find the tip deflection, that is the maximum tip, maximum deflection what we can obtain, and same time the maximum rotation. Okay, theta. And again, if it is a positive, because it is going to clockwise direction. So the visualization of the shape is more important. Okay, and here the maximum. If anyone asks the maximum, of course you know where you need to take. Okay, so I'm asking the tip. So what you need to do, you can use this equation at v over L and L time and x in here also v dash over L. So you can end up with your tip deflection at that's the maximum deflection and the maximum rotation at that point. At the end, this is a positive because of this clockwise direction. Okay, it's rotation of clockwise. Okay, this is the end of this question. So the most important things, we are starting from this general equation. So just this explanation, and here we need m, general m. So here this question we can express whole domain by using one bending moment equation. So then we can apply this one, and same time in here to here we have constant ei, so we can replace this one, remove this one, and we can do the whatever the other part like integration. So okay, so and after that you need to do integration and you will end up these values, and after that you will end up with constant integration constant to integration constant you can find by applying two boundary conditions. Okay, so you can see two boundary conditions like this. Okay, now we can shift to our second question. Second question again same problem, but my p is now apply a distance. Okay, so if you're going to develop the bending moment diagram, now I think you know this one. This until to here is like a cantilever. After that we cannot see any bending moment. Yes, you're correct. So actually in here we need to work with two bending moment values. You're correct. This is we have like a bending moment variation like this diagram. Okay, this diagram, and here bending moment is actually 0. You're correct. That means like directly we have trouble to use our equation. What is equation? This equation. So we had trouble to use this equation e I e double prime equal to m. There we cannot express this whole domain by using one bending moment equation. But again I'm asking, please try to develop your shapes. Then you can find a way of get rid of these kind of problems. So if you're going to develop this one, so into here is the cantilever shape, and after here there are no any bendings. So what actually happening? Same slope is going up to there, no changes. So what now we are interested about tip, deflection and rotation. But according to this arrangement, if you can visualize, you can simply understand, okay, this is theta. This theta should be equal to this theta because of slope is not going to change. There are no any moments. And if we need to find a tip deflection, simply you can think about geometric relations. So you know this is a theta delta c, and delta t is going to equal delta c plus you can use this arrangement tan theta c into this distance. Okay, this distance is L minus BA. Tan theta again is equal to theta. See, so if we are simply, that means if we can, so yes, it is correct. So when you come to here, so we don't need to use a two set of equation, one set of equation bending moment. We can predict this component, and other component we don't need to use the relation P I P double prime M, this relation. So from geometry, so we can predict it. So that means like we are going to apply this portion to this one, and this one we're going to use geometric relations. Okay, so that means one equation we're going to use it here. So that means we are not going to work with this connectivity, or actually we call this one to connectivity condition. So I'm not going to touch in here. So just we're going to deal with this one, and after that this part from geometry we're going to express. And when you come to the here, again I'm going to use, this is like a cantilever, same cantilever, only things you can see this is a length is A. So I'm going to directly use previous example relation. So previous example expression. So just what you need to do, A you need to replace by, so L you need to replace by A. In here L you need to replace by A. Okay. So now we can directly write down, these are two portions you can see, 0 to x component. So this is going to behave as cantilever, and this component again there are no any bending moment 0. Because of that theta is going to see, theta is not going to change, theta c, and respect to this theta c you can decide any place deflection based on the geometric arrangement or geometric relations. So now we can shift, and here what we can do, of course, we can use V prime, that means like a theta, and displacement of question 1 to obtain the result of part 1 by replacing L by A. So I already explained, this is for this part 1 question, part 1, and we can explain these two things, and you can get directly now this, I will clear this part, and this value and this value directly. Okay, so if you know this value and this value, next one you need to use geometric arrangement. I already explained this is going to equal to this part, you don't need to find directly, so you don't need to find again, and this is going to same value. And when you come to the here, so delta t is whole delta c plus delta x. So delta x equal tan t theta into this distance x minus a. So theta again, and theta is equal to c, theta c, because of small angle we are dealing with small slopes. And now we know this value theta c is this much, so you can put that value and you can add that part. Okay, so simply you can end up with this way. Again I'm explaining, this is, yeah, if anyone like to work with like a, it's like a two part, of course they can work it, but here simply you can see this is cantilever, and this is, you can predict the displacement based on these point values, so you don't need to find again another variations. Okay, this is example 2, and we come to the example 3. It is about again cantilever but distributed load, and here we cannot see point load, so you can start anyway means like a one, the most popular way of to note one is this manner with bending moment. For other ways you can end up with v o to the wx. Okay, so when you come to the here, I will explain in how to do in here. So in here again you can see you can express bending moment, general bending moment arrangement to whole domain, covered whole domain. So one shot you can do it, and you need to get like a portion. Again you can get the cut, and you better to think this side, otherwise you need to find this reaction. Yeah, of course they're not the very big things, and you will sum up, and you can, after that you can substitute these values and you will end up this equation. And after that you know what you need to do, two time integration. First time integration will end up your theta, and second time integration you will end up with like a deflection. If anyone like to work with this one, so he or she can work it, yes. And then to obtain this one, here we can see first integration constant, here we can see another integration constant. Altogether we need to work with like a 2 integration constant in here. That means you need 2 boundary conditions. 2 boundary conditions. But when you come to the here, you can see to obtain this thing you need 4 integrations. So 4 integrations means like you will end up with C1, C2, C3 and C4. So that means you need 4 set of boundary condition. Here 2 set of boundary condition, here 4 set of boundary condition. I will first explain this one and after that I will explain this one little bit, not fully, little bit about this one. Okay, now again what you need to apply? The same thing. So with respect to x you can integrate second one and you will end up with this value. Of course I'm not going to explain the integration. Again we are working with like EA constant cases, and this is second integration you will end up with here. So this is fixed end again, so you know theta and L at x equal 0, x equals 0 going to 0. So you can substitute these things to here and this thing to here, and you can find C1 and C2 and substitute, and you can find deflection variation and rotation variation without trouble. Okay, but if anyone like to work with this manner, so he or she need 4 set of boundary conditions. So what are this 4 set of boundary conditions? Of course we have like a 2 in here. Other 2 you can obtain from here. So you know from the free end, the free end boundary condition here, free end m at L going to 0 and V, sorry, not V, I will not put a V, so it will confuse you. M at L is equal to 0. Shear force, this is bending moment, and shear force at L is equal to 0. So these are, we can work with like this is third one, this is fourth one. So you can apply these things as another 2 set of boundary conditions, 3, 4, is a fourth one, third one, and you can resolve this problem also. Okay, but here I'm not going to explain. Of course you can try and you should end up with same results. Okay, so here you can apply and you can end up with, oh yeah, I'm explaining the third way, and you can end up with, here I'm asking the maximum. Actually tip deflection, again better to visualize first this one and get idea, then you can see. Of course the tip is this one, that's the point we can see the maximums. Okay, and you can substitute these values and at the L you will end up with these values. Straightforward. Okay, so the fourth one I am working with like a simply supported UDL, and this one also same, you can work with the both way. You can use either EIV double prime M or otherwise EIV 4 time Wx, because of we have only Wx. If we have any constant load, of course you need to add that one and delta function, but here we are not going to touch that area. Okay, so now in here I'm going to work with this manner. So then what you need to find, again the bending moment. In here again you can see, here to here we can express bending moment from one equation, one bending moment equation. First I need to find RA over RB, and symmetry it is going to equal WLO2, and you can get this small portion and you can find the equation or equation for M, and that is this value, and please substitute here and you will end up with this value. Again you need to do 2 time integration, you will find up theta and V. Theta you will end up with C1, theta V will end up with C2 and C1 and C2. So 2, again we need 2 boundary condition, either you can use this side or either you can use this side. Here the pin end, so you know in this side, so V equals 0 and here V again equals 0, and this is symmetric system. So at the symmetric point we know our prime rotation going to be 0. Here we have 3, but you can select any 2 and you can substitute and you can resolve the problem. Okay, and same time if you are going with this equation, that means E4 Wx1. So then you need 4 boundary conditions. So you already have 3 cases, and you already know at this point the bending moment arrangement. Of course, shear force we have, but the bending moment 0. So this is bending moment 0, and this is bending moment 0. So you can use those boundary conditions to find the integration constant under this category or this case. Okay, and here is straightforward, and same time here what we are after, maximum deflection. So when you come to the maximum deflection, here again if you can visualize this one, so simple because of this symmetry. So you know simply you should end up with the maximum deflection at x equal half of L. That time maximum, so that means theta should be 0. Okay. So otherwise what you can do, if you don't know those kind of visualization, so what you need to do, you need to find variation of v theta, and we need to find where we can see the 0 position, and after that find it about this value, and you can substitute to v and you can get the maximum deflection. Both are okay. That's the heading. Actually this is a function, fx function. If you need to find the maximum or minimum point, what you need to do, you need to find f dash x. So that means like a function fx, the derivation of function fx with respect to x. So and after that you need to equal to this one to 0, and you can find the maximum or minimum points. Here you can see, you know, first you need to put the range. This is 0 to L, and within that range you can find the maximum point or minimum point. It can be maximum or minimum. You need to find it is maximum or minimum. You know how to do this one from the first. Yeah, I think maximum, how to find the maximum or minimum point for given curve. Okay, so both are okay, or otherwise you can visualize and you can guess it. Okay, this is the maximum point, or otherwise you can guess it blindly. You can take out and you can take the first derivation of this, actually this is theta. This is theta now. First derivation of this deflection give the theta equal to 0, and where it's happening you can find the x value and you can substitute that to v and you can get the maximum deflection. Okay, and here I'm going with like a bending moment case. So then you can substitute here, integration will give this value, another integration will give this value. So you can use either, have like a mainly primary 3 boundary conditions, and you can select any of 2 and you can substitute and you can find c1 and c2. Okay, here we can find the c1 and here we can find the c2, and you will end up with the variation of v, deflection, and variation of theta. So theta, now from symmetry you know it should appear in the maximum point should appear in the middle, but if you don't know about those things, you can equate this one to 0 and you can resolve for x, and of course it will end up with f equal half of L for given domain. Okay, your domain is something like here now. Given domain you can find the maximum or minimum points. Actually here maximum point, because of we are taking this one as positive deflection. Okay, so that point, and after that you can substitute this value to here and you can get the maximum point. Here the visualization, if you can visualize, of course you can find directly and you can substitute. And here when you come to the equation, so when you come to the a rotation, so what you need to do, you need to substitute 0 and you can see it is positive, so that means it is a clockwise from your axis. And when you come to the here, if you substitute L, so you will end up with the minus value, so that means it should rotate in another direction. Yes, again if you can visualize this one beforehand, so you know the direction before you calculate these things. Okay, but if you don't know, and this will give the direction directly. Okay, so this is a fourth example, and in all these 4 cases we use only one set of bending moment. So we select the beam system and we select the beam system at any point of that beam section or beam system. We can express the bending moment by using only one equation. But think about this kind of arrangement. Now you know, in here when you come to the express bending moment, so this part we have different expression, and this part we have different expression, not same expression. So under this type of things, how are you going to deal? So now I'm going to use here EI, this equation. Okay, but you can see we can apply this portion to this equation to this portion. We call the left side, that is this is actually range, and this is the right side. This is the range A to L, this 0 to A, and separately, and we can end up with two set. But this is we know one set, one unit system. So how are you going to deal with this one? Give we cannot give two different equations for both sides, because this has a continuity at that point. So but actually I'm going to tell, of course this not going to bend or deflect like this, no. That means it's not going to happen this way, because of slope should be same, or other way it not going to bend like this one also. So deflection is same. So that means at that one, again the visualization most important. Of course in here we cannot see the maximum. This is not a symmetry, A not equal to B. Okay, think about this kind of arrangement, A not equal to B. In this case I am actually assuming B greater than B. So then we are expecting something like this. Sorry, something like this. So at that point, what we can see, the continuity condition. So continuity condition means slope both sides should be same, and deflection at both sides should be same. So we call this one to continuity condition. Now what we are going to do, we are going to derive equation for both sides separately. E I double prime M1 and EI double prime equal M2. And finally, we are going to apply this continuity condition. At that point, I will put at C. At that C point, this value should say at both sides. From that, I'm going to enforce this continuity condition for this equation, and I'm going to get like a one unit system. Okay, so of course first you need to find RA and RB. I'm not going to explain. And this side I'm going to use as a L side, left side, and this is the right side of me. And this is separately I'm going to derive the equation for left side and right side. And this is a equation, bending moment equation. This is a bending moment equation. Please again check these values. Okay, method correct, but please check the numerical or this symbolic values. Okay, now you just going to substitute this value. Same thing happening here, and you can do the two successive integration. You will end up with these two equations. I will put integration constant in left side, C1 and C2, here D1 and D2. Now you can see we have four unknowns. Here two unknowns and here two unknowns. But when you come to the here, so yes, we can. You are correct. So we can apply bending moment equation, but primarily we can see two boundary conditions. So we first apply boundary condition. Oh, otherwise actually we can apply later. The other one what we going to use actually in here is continuity condition, because we need to enforce this one. So because of that we need to use these two conditions. That means from this side and from this side, if you come to C point, deflection and rotation should give the same values. So first I'm going to use that continuity condition. At x equal a, slope should be same, so I'm going to use this equation. From that Q, C1 should be equal to D1, and this one gives C2 equal to D2. Now we need to find only two set of equations, so two set of integration constants. So for that I'm going to use this primary boundary condition at that point and that point. So I'm going to find it, and here when you're going to use it, boundary condition, apply the boundary condition. Here first I apply the continuity condition. From continuity condition we realize these relations, and the next we come to here, apply boundary condition. So then first boundary condition give this value C2 equals 0, that means D2 equal to 0. And the next second boundary condition, x equal to deflection must be 0. Here also deflection should be 0. You know this one, this is a pin end, deflection 0, and roller support, deflection at 0. And this one D1 and D1 give this value. and you will end up with the C1. Here again I need to explain this one clearly, and this is of course you can understand, but when you come to here, so this is x equals 0. X equals 0 means your left side. Okay, so you need to select left equations. Okay, left equation, this one. When you come to the sorry apply boundary, when you come to the x equal L, that means you are working with like a right side. So then you need to select a right side equation. Okay, right side equation, sorry, so this right side equation. Okay, so you need to apply, so you need to careful about now the sides. Okay, based on your domain you need to select. If it is within this range, so you need to work with L equations. Means in this range you need to work with like a right side equations. Okay, come to here. Okay, we know these values, and now you can substitute and these values, and you can actually, this is a direct substitute, and after that you can rearrange your equation. You will end up with, this is a left side rotation, this is a right side rotation, this is left side deflection, this is a right side deflection. And now I like to obtain the angles. So if you're working with this angle, then you need to work with L side equation. If you want to work with like this angle, so you need to work with like right hand equation. So you can substitute and you can end up with these two equations. Of course, this is positive angle and this is negative angle, because of it is going in clockwise direction. Okay, and the next important thing, the maximum displacement. So when you come to the find the maximum displacement deformation, here of course if it's the middle, then the symmetry, you know it happened in the middle, but is it not a middle? It's not equal to A, not equal to B. So I'm using this arrangement. It can be A greater than B or B greater than A. Yes, you know, if you know this system, so you can solve this one. So I'm assuming this one, A greater than B. Then if it is A greater than B, from practical experience, you know, and then your maximum point should lie between this range. So that means, think about here to maximum point distance. If it is xm should be less than this value. Okay, so that means like the maximum going to lie between this A and C point. Okay, so now considering this one, so you're going to find this one. So this is the way maybe maximum deflection will occur left portion. That means A should be greater than xm. Okay, this is actually assuming. So we can double check after our calculation. Again, this one is okay or not. And what you need to go, you need to find the zero rotation. So actually this is a function, fx function. Actually that function is your v function. We need to maximum point of this v function. Then what you need to do, you need to find fx and equal to 0. So that means we need to find f dash x equal to 0. So f dash x is like, it is directly rotation, so rotation going to equal to 0. And careful, we are working with like a left side, so you need to find the left side equation, and this is equal to 0, and you will end up with xm at that time equal to this much. So you can double check this assumption is correct or not. How you going to double check? So this is a value, I'm taking xm now this value, so you can put to here, and I'm squaring both sides. So then L squared minus m squared divided by 3. So that means 3a squared should greater than L minus a, L minus a, L plus b. You know this arrangement, and this is a. So a is going out now. 3a greater than L, again a plus b. So then this is a plus 2b, and if you go into 1, this is a to a, that means a greater than b. You can see it is okay. This is our assumption. So based on this one, we assume this part. Oh, based on this one, we got this value. So you can double check it, it's correct or not. Okay, so you can end up with this point. We can see That means this point we are expecting maximum value. So then what you need to do, we can substitute this value to your VL equation, and you will end up with this value. Please check again the values. Okay, and after that we can show the arrangement. Of course, this is a theta, we already calculated this one. This is again positive, this is negative, and maximum point lie between this one. So you will end up with this one. This is different from your previous example because in here we work with two parts, two separate parts, because we cannot express our bending moment variation from one particular equation, one equation. We use here two set of equation. When you come to the two set of equation, we need to create continuity. So to establish that continuity, we are using continuity conditions, and here we are using two set of continuity condition V and theta. Okay, and this is the end of our session today. So the next class or next session we're going to touch about Macaulay square bracket notation. Actually, this is basically work with mathematics, and this one we're going to discuss under this category. This section we're going to discuss about if we have this kind of arrangement, how we're going to deal. Now you can see if we have this one, if you go in conventional manner, so you need to derive two set of equation, and after that you need to enforce this continuity conditions. But the problem is coming because we have a trouble to express one bending moment equation for whole this unit. If we have any way of doing that one, that means like if we have any mathematical way or mathematical tricks to express the bending moment diagram or bending moment one bending moment equation for represent whole this part, then we don't need to apply these kind of two sets. So this Macaulay bracket or square bracket notation actually we're going to use for remove that difficulty from this kind of arrangement. Okay, so next session we will going to touch this one, and we going to discuss about the equations. So we're going to discuss about the examples. So until that, so thank you very much, and please ready for these things. And square bracket notation, I will explain these things, and so I will explain, and after that here I have like again like a 5 to 6 example. I will explain how you can use this square bracket notation to express your bending moment for different if you have like a different cross section, how you're going to use one particular equation by using this square bracket notation to express the bending moment, and after that how you're going to use this integration operation for those kind of things. And the next final part is moment area theorems. Okay, until that, so I'm going to stop. So thank you very much.